All right. We're still talking about basic organic chemistry, and you guys have seen some supplemental videos that I think they're pretty well produced. And when we, or the stuff I was making, the stuff I've been writing here on this Windows whiteboard, the last thing I talked about was benzoyl peroxide, and I talked about how it can be a cross-linker for polystyrene here. And I'll kind of draw that out for you because I'm trying to relate, kind of going over basic organic chemistry, which some of you may or may not have had, and really kind of make it as helpful to the subject matter of polymers as possible. And so we have benzoyl peroxide, 2 arenes on either side, and if we have polystyrene, we have our little arene, and I'm kind of keeping a lot of the stuff I draw simple because it would take kind of forever, and I'm not that great at drawing at all, so I can't really use this Surface tablet as an excuse. But I guess I want to call this nomenclature. There's probably a better word for this, but when you see the little squiggly line, that means it's a chain. We've done this nomenclature before, and you could do, I'll just do polyethylene. And you saw it just above, but I'll write it out anyway. Also means it's a chain with the N. So that means there's multiple MERS linked in a chain to make a polymer. So we have an arene here. This is polystyrene. Oops. So this is polystyrene, and then we have benzoyl peroxide. So what happens is the benzoyl peroxide, did I draw that right? Oops, no, I didn't. Dope. Homer Simpson. Let me fix that. At least I caught it. Okay, 0, 0, come on, man. The benzoyl peroxide basically acts as a crosslinker. And we'll see this again, but I kind of wanted to write it out. So we have this chain of polystyrene and this chain of polystyrene, and it's cross-linked by benzoyl peroxide. And kind of ask yourself, what does this do? So if I have polystyrene chains, just kind of just laying around versus a polystyrene chain that's linked somehow with another polystyrene chain, ask yourself what this does to mechanical properties. And cross-linking in general, kind of ask yourself what it does to mechanical properties. And we'll cover it a little bit more in detail, but when we're going over basic organic chemistry, I want you to immediately kind of tie it into polymers. And so we have peroxide. It's basically on the subject of adding oxygen to organic compounds. So it's an oxygen-containing organic compound, as I've written here in my My Little Pony rainbow, which is, I kind of love it actually. And epoxy, another oxygen-containing organic compound. This becomes very important, thermoset polymers. And then peroxide, so benzoyl peroxide, so ends up being a cross-linker. Okay, so think about that. The next thing we're going to talk about is this group. And some of you may already know what this is, and that's cool. Carbonyl group. Is what we call it. And I'm going to go ahead and highlight it so it looks pretty. So a carbonyl group. And carbonyl groups, maybe some of you have heard of formaldehyde. And so if we have an aldehyde, oops, made a mistake, didn't switch pens. If we have an aldehyde, it's O. And so we have a hydrocarbon here and a hydrogen here. So this would be an aldehyde. Am I spelling it right? Yes. Spelling is extremely important because changing one letter can change a lot of things. Okay, so if we have a hydrocarbon here and then a hydrogen here, that's an aldehyde. And formaldehyde is one as well. Another carbonyl group, if we have two hydrocarbons and kind of this carbony tail, this would be a ketone. So ketones are another kind of, I don't know, I want to say important compound. All right, so we have an aldehyde and a ketone. My brain got off or something, so I said formaldehyde, but formaldehyde would be this. So this is generally a hydrocarbon, but I guess kind of close enough. So formaldehyde is considered bad. It ends up in a lot of polymers as well. It's a preservative, I believe, for frogs and stuff like that. Kind of other aldehydes kind of take a segue because chemistry is fun. Again, I'm not a chemist, as you can tell, and but I have an appreciation for stuff, and we do a lot of cooking in my house. And so we're talking about aldehydes and or carbonyl compounds. Actually, not aldehydes, but we're talking about carbonyl compounds. And if you look at this, I believe that's correct. This is a carbonyl group or carbonyl compound, but this is cinnamon. And this is an arene, but it's an aromatic, right? And what is cinnamon? I think it smells good. So we're kind of tying two things that we've talked about before. So we have a carbonyl compound, also has an aromatic on the end, smells good. Does it really have much to do with polymers? No, but we're kind of talking about basic organic chemistry. Another carbonyl containing group is it's a pretty somewhat of a complex molecule. They draw the benzene right, yeah, or arene right. Kind of butchering the structure. Anyone who's a chemistry major, I think, gives a, oh man, when I do this stuff. And then let me draw it so we see the carbonyl group a little more plainly. So this whole thing here is the hydrocarbon. This is the hydrogen. And sorry, went way too far up. Come on, i7 processor. Oh my gosh, went way. Might edit this out, maybe not. So carbonyl group. So we have a hydrocarbon and a hydrogen on the other side, so that's an aldehyde. And someone may argue with me against this, but that's fine. How did this get circled? Oh yeah, sorry. This is the R. I circled it. Oh my gosh. I think this is an aldehyde, but this is vanillin. Or vanilla, so that's why vanilla smells good. So again, another aromatic carbonyl containing compound, and so that's kind of cool. There are several other carbonyl containing compounds that kind of become more pertinent specifically to polymers. All right, so the next thing, so we talked about adding a carbonyl group, and so you get aldehydes and ketones, and ketone, again, 2 hydrocarbons on either side, so several, we'll get into ketones a little bit later, and kind of how that relates to polymers. We talked about carboxyl containing groups that have aromatics with them, so cinnamon, really smelly and good, tasty, and vanillin, I like it, you may not, but it does have an odor. I think, even if you don't like it, you can recognize that vanilla and cinnamon have an odor. Where I live, we have these gnats called chiggers, and chiggers I think they're gnats, but they bite. And kind of talking about it, why? Because vanillin, the only way to really repel them is vanilla. So kind of food for thought, useless trivia. But anyway, chiggers, these gnats, they get you, they bite. And anywho, vanilla is good. The next thing we want to talk about is carboxyl group. And carboxyl groups are very important as well to polymers. And a carboxyl group, if you combine a hydroxyl group with a carbonyl group, you get a carboxyl group. And so this is carboxylic acid. Can't spell it. And carboxylic acid or carboxyl acids are really, really important. And one thing, I'll kind of give a preview, and we'll talk about it again. I'll show you this structure. Sorry. Can't draw these things very well, and I apologize. I should find some software or something to help me draw these, present this a little better. But I'll push forward. So this is a benzene ring, and on this one we have And on this one, we have all right, so it's understood at this inflection point that there's a carbon, and I'll go ahead and draw it there. Okay, and if we remember the numbering convention from the videos that were out there, we have 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5, and then 6. Okay, so these are the different positions of the carbon. And so this is called 1, 4, and there's a benzene ring. So and then there's 2 carboxyl groups. Okay, so oops. So 1,4-benzene man, I'm embarrassing myself more than usual. 1,4-benzene dicarboxylic acid. Okay, this guy here. When you combine 1,4-benzene dicarboxylic acid with ethylene glycol, you get a condensation reaction. So you get a condensation reaction. And then what you get is PET, basically. So it's polyethylene terephthalate. And it's very common. It's what's used in drinking bottles and that kind of thing. And what else is it used for? Your shirt. If you have a polyester shirt, this is generally what it is. So PET isn't the only polyester. And when we talk about how this reaction occurs, there's a chemical reaction called esterification. And that's where the ester comes in polyester, and the fact that it's a repeating macromolecule or mer means it's polymer. So polyethylene terephthalate. And always spell it wrong. And we do a lot of recycling of this stuff in the lab, several projects with that. So polyethylene terephthalate. Drawing our benzoic acid structure, and I'll draw for whatever reason, I always think of Legend of Zelda when I draw a benzene ring, or my interpretation of a benzene ring. All right, so benzoic acid, which is actually in dark alcohol drinks or spirits, right? Like gold tequila. That kind of thing. Benzoic acid also featured in one of our supplemental videos. A little bit different, right? So this is 1,4-benzene dicarboxylic acid. We have a carboxyl group specifically at the 1 and 4 position here. You could perhaps call this 1-monobenzene, or one what would I call this? A 1,4 benzene dicarboxylic acid. You would call this 1-benzene monocarboxylic acid, perhaps. I don't know. I would never make it as an organic chemist, I don't think. But anyway, benzoic acid, simpler group. And the most simple would be carboxylic acid. Oh, you see all the notes in one shot there. That's kind of cool. Kind of moving on. Let's see, where do I want to move on to? We talked about polyester, peat, and polyethylene terephthalate. So this is, it's not the only polyester, but usually when people are talking about polyester, it's this stuff, the stuff that water bottles are made out of and that kind of thing. And kind of all over the place a little bit. But esters, kind of a general ester group, tends to look like this. And with a hydrocarbon here, a hydrocarbon here, carbon there, and I messed up this guy. Hold on. So differs from carboxyl groups because instead of a hydrogen on the end of that kind of chain, so instead of having the hydroxyl group, you have an oxygen and then another hydrocarbon. Okay, so we have a hydrocarbon and another hydrocarbon. So this is an ester. So it's a little bit different than a carboxyl, like a standard like carboxylic acid. So it's an ester, but you still kind of have a carboxyl group because kind of like we talked about here, the carboxyl group is really, I kind of made a mistake when I drew it that way. With the bond. So this is really the carboxyl group. So you can substitute different things. So you generally get a hydrocarbon here. You can put a hydrogen here. So if you put a hydrogen here, that's carboxylic acid, kind of like what we had up here, where I said that this is a carbonyl group. And a lot of times people say this is a carbonyl group, and it's true, it's one of the carbonyl groups, but the kind of real basic structure, you don't designate whether this is a hydrocarbon or a hydrogen. And so I didn't repeat that. And different texts kind of do it a little differently. This is kind of how I do it, actually. I just call it this because it's easier for me. But anyway, carboxyl group. And so that's why we can kind of substitute different things. So now we have an ester. And common ester is ethyl acetate. Did it again. Sorry. So ethyl acetate. And so we would have this structure. And ethyl acetate is kind of interesting because we have a methyl and ethyl group, but it's ethyl acetate. And the reason why it's ethyl acetate, I'll get to in a little bit. But this would be a methyl. And this is an ethyl group. And so this ends up being an acetate group. This whole thing here is the acetate group. And it's kind of interesting because we have like polyvinyl acetate being a pretty common polymer. It's otherwise known as like school glue or white glue, like Elmer's glue. And hold on 1 second. I say this is the acetate group because acetate is a CH3 COO. And so the acetate molecule would look something like this. Oh. And I think this is what it would look like. And anyway, so I'm saying this is the acetate group because this CH3 is really a methyl group. And so I substitute methyl there. So acetate, we have polyvinyl acetate. And so polyvinyl acetate, there's polyvinyl alcohol and polyvinyl acetate, and both used as glue. Incidentally, both polyolefins, and we'll talk about this again when we talk about kind of basic polymers. But again, trying to relate the organic chemistry with basic organic chemistry with polymers. So this is 3. And acetate vinegar, acetic acid is vinegar. And so this is PBA. It's a white glue. If you add glitter to it, you get glitter glue. So just kind of throwing that out there. The next thing we want to talk about is adding nitrogen. And let me change it back, sorry. So adding nitrogen. And when we add nitrogen, we basically make an amine. And so polyamines are nitrogen-containing polymers, basically. I'm trying to get to 100%. And an amine is hydrocarbon, nitrogen, hydrocarbon, hydrocarbon. So it's becoming a more complex structure. So polyamine would be one. Different nitro or nitrogen containing compounds, we'll kind of want to do some terminology. And so nitro is hydrocarbon with NO2. Gonna make the car go fast with that, right? Fast and furious, but and I'm getting weird response from my screen here. Diazo is hydrocarbon, nitrogen, triple bonded to another nitrogen. And nitrile, which very, very big in polymers. We're all wearing nitrile gloves in the lab and maybe outside given the times. But nitrile. And so a nitrile group is hydrocarbon bonded to another carbon, which is triple bonded to a nitrogen. And this one we'll definitely see again acrylonitrile being one of the ingredients in ABS, and we'll definitely look at this again. So nitrile is more of a polymer related thing. This is also nitrodiazo. So don't forget these terms. So nitrodiazonitrile, these are different nitrogen-containing organic molecules. The other thing that we're going to talk about in terms of nitrogen-containing organic molecules are amides. And an amide structure is this. So you have nitrogen with two dangling bonds. So this is an amide structure. And so polyamides are very strong. So this amide structure also becomes pertinent, very pertinent to polymers as well. And what else do I want to say about amides? It escapes me at the moment. But amides, so this type of structure, polyamides are a strong polymer. Sulfur containing, now we'll move on to that. Sulfur containing, and sulfur containing thiol would be a hydrocarbon with a sulfur and a hydrogen. A thioether, and I don't know if I should have talked about ethers. Yeah, I did talk about ether earlier. So if you remember back up here, where we talked about, man, we've talked about a lot of stuff. So that's good. Epoxy ether. So ether structure was hydrocarbon, oxygen, hydrocarbon. And so this is diethyl ether. So ether group, oxygen ether group. We have another, oops, what the heck? There we go. I guess it, when in doubt, just hit it. And, oh, come on now. Killing it. I didn't know I could move my scribbles. Excuse the delay and going back and forth, folks. Sulfur containing. So thiol was one. So thioether. There we go. Oy, come on now. Killing it today. Oh, come on. Will I edit this out? Probably not. Sorry. I apologize, actually, in all seriousness. There you go. So if I can draw it finally, thioether. Kind of shrunk my pen a little too much. Why are you doing this to me? And then why aren't you minimizing? Because everyone's going to see when I did this. But that's okay. All right, so cleared up a little bit of technical difficulties there. And we're talking about thioether. Oops. And instead of an O in the middle, it's a sulfur. And some people denote it as R prime. And so I've said R is hydrocarbons. R prime sometimes means it's a different hydrocarbon. And earlier I said that R is hydrocarbon. It can also be hydrogen, which kind of confuses things, actually. It kind of bugs me. It can also be hydrogen, and I've been reading around, and then some people say it also stands for any. And in my memory, I was always taught it was a hydrocarbon, so maybe I was taught wrong or something, or I just remember it wrong. Anywho, so thioether is another one. Thiol ester. So that's a thiol ester. Sulfoxide. And some of these become more important. We'll definitely talk about sulfur when we talk about vulcanization of rubber, and because that was kind of a big deal for tires and the like. And so our, and again, sulfur containing hydrocarbons is what we're talking about. And then sulfonic acid. And hydrogen. On the subject of abbreviation of letters, so we said that X is a halogen. So X is a halogen, and oops. So R, come on, making a boo-boo, would be this structure. And so like a halogenated benzene or halobenzene. And so where this is any halogen element. And so halogen, if you remember, is chlorine, fluorine, bromine, and iodine, right? And if we look at polyethylene, right, and I can be proper and do the N. If we halogenate it and we knock off this guy, replace with chlorine, we get, wow, it dropped down. That's okay. So chlorine atom is much bigger than hydrogen, so that kind of adds a strengthening effect. This is PVC, so polyvinyl chloride, which is a halogenated alkene. If we think of it that way, alkane, sorry. But anyway, oops. All right, hold on. Halogenated olefin. So halogenated, so halobenzene could be any halogen we put there. If we halogenate, excuse me, halogenate polyethylene, we get PVC. Pretty common actually. So this is just vinyl. So records, that kind of thing. So we're going to move on. We're going to move on with kind of basic organic chemistry. Hopefully this is useful. And I'll also have some other supplemental lectures for you to look at.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.